Attends, je t'ai vu. GDR, ils t'ont invité, GDR Sécu.
Oui.
On a fait la semaine dernière.
Donc, vous avez...
On était à Londres.
Ouais, la semaine dernière.
En plus, j'ai fait une typo. Le fichier s'appelle claise.txt.
Moi, j'avais écrit Blaise avec un Z pas mal de fois, je crois aussi.
Oui, j'ai vu une fois
fait des
sur le
conneries,
site.
Désolé. Hein.
Non, non, il n'y a pas de souci. Quelle heure il est 9h23.
Je vais prendre un micro.
All right.
Yes.
Welcome back. We are going to start this edition's second day of the conference. The first talk is going to be a keynote, and we are happy to host our two speakers who are Agathe Blaise and Jacopo Bufalino. I'm sorry for the pronunciation. So they, respectively, Agathe is a research engineer. So I have my cheat sheet, because I don't know everything by heart. I'm sorry, so I'm going to read that. So Agathe Blaise is a research engineer at Thales Company. She received a PhD degree in computer science in 2020. Her research interests focus on data analysis applied to network security, and more especially intrusion detection, cloud computing security, data dissemination, management, and quantum networks. Jacopo Bufalino is a research engineer at Conservatoire National des Arts et Métiers, le CNAM. I'm sorry, I'm lost. Yes, and a doctoral candidate at Aalto University in Finland. He previously worked for several years in DevOps and DevSecOps. His research interests include cloud network security, container security, and software supply chain security. So today, they are going to delight us with a guest talk, a keynote, I'm sorry, who's titled Supply Chain Security in Kubernetes. The floor is yours. Thank you.
Thank you for the introduction. So hello everyone, and welcome to this talk, where we will talk about the supply chain security in Kubernetes. So first, thank you for the invitation. We are very happy to be here. And today with me there is Jacopo.
Hello. I think we were introduced already, but once again, I'm a doctoral candidate at Aalto University, and right now I'm working at the CNAM.
And my name is Agathe Blaise, so I'm working at Thales 6. So during this presentation, we will be mainly talking about Kubernetes. So in this room, please raise your hand if you already used cloud-native technologies. Okay, great. So as you know, Kubernetes transforms the way we are deploying and managing the application. And within comes an increasing complexity to manage the application, but also to manage security. It also comes with an increased surface of attacks. We have new attack vectors. The isolation is only made at the software level. So it introduces new challenges to secure the software supply chain. So today we will be speaking about those challenges to secure the software supply chain. And then we will dive into three topics that Jacopo and I studied. So first we will study container vulnerability scanning and software bill of materials. Then we will look at the Kubernetes application and the configuration of the deployment, in particular looking at security. And finally, we will look at network misconfiguration in Kubernetes. So first, very brief introduction on the containers and virtual machine. A virtual machine offers a complete way to emulate the systems, meaning they emulate the hardware, but also the operating system. So they are heavier, but also more secure, because they provide a strong isolation, while the containers only contain what the application needs to run, so libraries and dependencies. So they are, they are lightweight, but at the same time less secure, because they share the same system. So if one container is compromised, it can lead to compromising other containers or even the whole system. We also have Kubernetes that manage the infrastructure with code. You can use code to manage your infrastructure, whether instead of deploying several scripts to manually configure your application. This is infrastructure as code. And finally, we have declarative files where you define the real final state of your systems, and the controller will try to enforce these states. So now we will study the DevOps pipeline that we can set up to automate the building, test, and deployment of the application. So first, we will design the application codes that lies within the containers and build the container image. So typically, we can download images from external sources like Docker Hub repositories. So we will have to trust the source and verify the image. We can run unit tests, generate artifacts for the containers. Then we will have the Kubernetes manifest that contain all of the application, bundling containers within pods, and other resources like the accessibility of the pods, the secrets, the volume, security context, and so on that we will study. We deploy this into production, and finally we have real-time monitoring, data collection, and logging. But what can actually go wrong into this DevOps pipeline? First, we must analyze the source code within the container image for vulnerabilities. So this will be one of the topics of our work. We also need to analyze the configuration and the security context of the Docker image, especially if it comes from an external source. We have to look for tamper dependencies and verify artifacts. Looking at Kubernetes manifests, we have to look for misconfiguration. We can have pods with too much privilege, with exposure to the outside and to other services. We will study supply chain attacks, and finally monitoring can be vulnerable to zero-day attacks or undetected breach. And so if you received this magazine, the MISC magazine, you have seen that there is a great article on the Cyber Resilience Act, and this is actually one of the main motivations of our work. So it is a recent regulation that aims to establish common standards to improve the cybersecurity and cyber resilience. So the objective is to bring products to the market with less vulnerabilities and to maintain their security throughout their whole life cycle. So we have several key parts. The first one is security by design or by default. So we will try to minimize the risk and to reduce the surface of attack. We want to establish software bill of materials, to know the list of packages within the application and to be able to discover vulnerabilities, and finally to provide security updates regularly. So in our work, we aim to automate this process of building by default secure configuration by being adapted to the system, and to increase the transparency and security of those products. So we have different challenges while securing the software supply chain for Kubernetes. We must rethink the security compared to traditional models, meaning that security practices that apply to static and monolithic systems don't apply anymore into those dynamic cloud-native environments. And we have new security risks, which are induced by the virtualization and the isolation being made only at the software level. We have new attack surface like container escape, host kernel vulnerabilities, and misconfiguration at the orchestration layers. And we saw that typically manually defining security policies in such a dynamic environment is really hard, because most of the time what you think you are enforcing is not what you are actually enforcing. This is partly because of the declarative approach, where you may define several things. One example is to define one security context for the pods and for your containers, and the one from the containers will override the one from your pods. And in fact, we can model the supply chain attacks that can arise in a Kubernetes cluster, and we can see that a single vulnerability in a container image or in the platform itself can escalate to full system compromise. So these are several tactics from the Mitre attack matrix designed for Kubernetes. First, we have the initial access. So we can take advantage of a vulnerability within the container image. We can be a malicious Docker image or a vulnerability of the orchestrator itself. Then once the attacker gains access through remote code execution, for example, it can open a reverse shell, and it will try to discover the resources running in the cluster, so listing the list of overpods, the list of secrets, And in particular, it can try to elevate its privilege. So to do so, it can use a vulnerability and trying to get root access. It can also try to move to another pod with more privilege. And then it will try to evade a detection engine to be persistent, meaning if we restart the container of the pod, it will try to escape these containers to be persistent to the action of the administrator. And finally, it can try to steal or to compromise user data, to launch denial of services, or to create new outside workloads. So to counter this, Kubernetes implements several security best practices, different than Docker that just runs containers. So we have policies related to networking. We have network policies that are firewall rules between the pods. We also have authentication and authorization with role-based access control, where we can define service account tokens and different roles for each pod and each user. We have by default encryption with TLS of the communication and of the secrets. Those secrets are stored in a specific location, which is the etcd database. And finally, we have security context applied to the containers and pods with possibly AppArmor or second profiles. So now, diving into the Kubernetes security supply chain, there are still some challenges that we would like to solve. The first one is during the build. We will build the container image. So at this time, we can provide image scanning. So we will describe a first contribution on the container vulnerability scanning. Then the second step is to scan the configuration of the whole Kubernetes application with all of the resources. So we will try to reconstruct a graph and to reconstruct attack path from an attacker. And finally, we will have a look to container runtime and analyzing microservice connectivity. So now I will give the floor to Jacopo that will talk about container vulnerability scanning.
Thank you. Hello, everyone. So let's begin our journey by understanding a little bit where we are. We are at the build step of the supply chain. Means that our source code was built, tested, and packaged inside a container. Now, what we want to do with this container is to make sure that it has zero or close to zero vulnerabilities. And this is why? Well, the reason is that first, many of the vulnerabilities that happen along the supply chain, they are actually due to outdated or vulnerable dependencies, mostly stored in containers. And it is very important to catch them as early as possible in the release process, because we don't want to have vulnerable component hanging around in our production servers. What is the industry focusing on right now? Everyone is super scared because of the new regulatory framework. So companies are mandated to have these documents describing their dependencies and software. And usually when we scan for vulnerabilities in containers, we'll see a long list of CVEs. And not all of them will actually apply to all the applications. For instance, I have a Python application. Why should I care about Perl CVEs? So that's more or less what's happening right now in the industry. And we will start our journey by discussing a little bit how this container vulnerability scanning works in practice, what are the files that are scanned, and then we will take a look at our contribution. So container vulnerability analysis usually can be divided into two steps. First step, we have file system indexing, where those tools will go through the container file system looking for files with interesting names or extensions. They will also do some regex-based search on, for instance, licenses or authors inside the files. And at the end of this step, we're going to have a file, the so-called software bill of material. Then this same file and the package information inside that file will be used by this tool to find vulnerabilities in dedicated databases, like the National Vulnerability Database or the GitHub Advisory Database. Although many times, these tools, they build customized views over those databases for a faster lookup. What do container scanners look in practice? So as said, they look for interesting paths or regular expressions. They look for operating system information, operating system, package manager information, programming language dependencies like requirements.txt for Python or package log.json for Node.js. Then they can also look for metadata files like this info/metadata. Those are files that tell the content of a given dependency for an application. And last but not least, we have binary metadata. Some of the latest compiled languages like Go embed information about the dependencies inside the final binary. And here we are to our contribution. So what happens if some of those files are accidentally or non-accidentally removed from the container file system? We call this container obfuscation as the act of modifying or generating a container image that doesn't have package-related information. So what we did was that we started thinking, what are the different ways a container image can be modified? And we went through looking at different tools, white papers, industry standards, and we came up with a list of 8 techniques, obfuscation techniques. I'll go through them quite quickly. So we have operating system and operating system package manager obfuscation. We basically delete or modify the file containing the list of packages that you have installed in your computer. Like you delete the dpkg/status file. Then we have a similar operation that can be done with dependencies or dependency metadata files. Continuing, we have the URL obfuscation, where basically instead of installing software using package managers, you do it directly from source. Then we have alias and link obfuscation, where the creator of the application would use aliases or links to remove, to obfuscate the real name of a binary, for instance. And finally, we have a pack obfuscation, packing. We would use multi-stage builds or other tools that compress the content of the container image. After that, we had to come up with some tools to test with against obfuscation. We selected 6 of them, 3 open source and 3 cloud proprietary ones. We select the Google Artifact Registry, Microsoft Defender for Cloud, and Amazon Inspector. So we have the tools, we have the techniques, how to test these tools. We need a dataset. So we created our own dataset of increasingly obfuscated images. We started by single instances of obfuscation, and then we combined multiple instances at the same time. And then we scanned the images using these 6 tools. Results are here, and I'll try to help decoding them a little bit. So what we see here on the first part of the table is that every tool is vulnerable to at least one type of obfuscation. And the more obfuscations at the same concurrent obfuscation, the less packages and vulnerabilities these tools will find. Interestingly enough, some cloud provider tools like Amazon and Google Cloud will even not scan images if they don't have specific files, creating all sort of like visualization problems. So now we know that obfuscation can happen and tools are vulnerable to it. But does it happen in practice? Let's test it. So we created a list of 600 Docker containers from 6 different datasets, some used by hobbyists, like what I would use for my own cluster at home, and others from that are meant to be run in production. We basically looked at different files and modifications in the container file system, and our results show that obfuscation is happening on every type of technique. So all the techniques basically have some sort of most of the containers have every type of obfuscation. The most used one is the OS package manager obfuscation. This is mainly because containers used to run this apt-get update as a first command, but other times before doing that, they can actually install binaries with outdated dependencies. Let's take a look at the real world example. So this is an extract from a PostgreSQL container image. We have a single run command in the Docker file that starts by downloading all the dependencies, then downloads PostgreSQL from the internet. From the internet, and then it downloads some plugins for Postgres, and then deletes all the dependencies. What happens is that at the end of the day, the container layer will be left with 3 binaries that are impossible to get scanned with the state-of-the-art tools. So what we did, we started thinking about a solution to this, and we built our own methodology that we call Orca. And the way it works is basically that we scan every layer individually, trying to create a sort of Git repository out of the container image, and on top of that, we also reconstruct the original Docker file by accessing the container's metadata. And based on that, we try to improve the file system coverage, meaning that we try to analyze and scan as many files as possible. And the source code is available here using the QR code. Finally, we run the same sort of initial tests that we had before also with Orca. And as you can see, Orca is resilient to many types of obfuscation. We have still three cases where we're not doing that great. And that's because we have the package obfuscation that effectively deletes the history of the container, so we cannot reconstruct any information. This is it for this first zoom. Now let's look at Kubernetes configuration scanning with Agathe.
So now that we've seen the scanning of containers, we will have a look to wall configuration of the Kubernetes application. So this is the second step in the Kubernetes security supply chain. So typically, when we try to deploy Kubernetes application, we can download Kubernetes manifest or Helm charts from Artifact Hub that will combine different YAML files describing all of the resources needed to run the application. So this will include the pods and the deployments containing the containers, but also the service accounts, the service policies, the permission of the users, network policies, and so on. And these are very complex and long Kubernetes manifests to scan for security misconfiguration. So we have several benchmarks, like the Center for Internet Security Kubernetes benchmark, which is a reference, and which will give a list of guidelines to respect to avoid misconfiguration in your Kubernetes manifests. So these tools execute compliance checks with regard to these best practices, but the output will be rather a flood of micro-suggestions that you need to fix. And we have no big picture of the global security configuration. We don't know which ones are important to fix, which ones have a real impact, and most importantly, how they can connect together for an attacker to leverage different vulnerabilities and escalate to full system compromise. So we wanted to better understand the connectivity between each configuration and to have a global picture and evaluation of the level of defense of the configuration compared to different attacker tactics. So we deployed methodologies to do so. So this is how a configuration file is done. So we have first the Docker container image with the reference for the image and its configuration. We have its Kubernetes pods, which contain the main applicative containers and optionally some sidecar containers. And we have various resources that will help define the Kubernetes pod. We have the namespace that provide isolation between groups of resources. We have the services of the pod, so the accessibility. We have the service accounts and roles, so the permission that a pod is allowed to do in the cluster. The security context, which allows to define several security configurations, like whether the pod can run as root, whether it has access to given files, it can run several Linux capabilities, AppArmor, second profile, and so on. So this is very important. We have the network policies that are firewall rules, and finally, the secrets that may contain sensitive information and volumes. So in our analysis, we want to first have a look to the configuration from individual pods, making different security analysis. So we can look at the reachability of the pods, seeing if it is accessible from the outside, for example, for a web interface. We also have a look to container image to see whether they contain high and critical severity vulnerabilities, and in particular, remote code execution for an attacker to open a reverse shell in the container. We have a look to the security context, having a look to run as root for the pod, having a look to links capabilities, the file permission, the permission to launch privileged containers, to use the host machine networks, or to have a partition mounted on the host platform. So all of these are security configuration defined in the Kubernetes manifest. And finally, the service accounts and permission of the users and the pods, like the possibility to create new pods and workloads, to create or to list secrets, and finally to execute other pods. And once we've done this security analysis for each individual component, we will try to look at the connectivity among those pods. So we want to understand whether an attacker can move from one pod to another. So to do so, we look to firewall rules between the pods, to the pods affinities that may say that two pods must be collocated on the same physical or virtual machine, on the contrary on two different machines. And finally, there are some permissions that allow a pod to execute other pods. So using this different analysis, we try to reconstruct a model as a topological graph of nodes and edges. So nodes are pods and containers within the deployment, and edges are the relation between those different nodes. So first, here we have the graph with pod and containers, and we have a list of Kubernetes objects that relate in some way to Kubernetes pods. So we can use selector to map those objects to the original pods, and we can have a look to all of these different objects. And the objective of looking into this object will be to lead several security analyses. So we will have a look to the vulnerability scan of the containers, whether we have critical severity vulnerabilities, whether we have opaque containers that cannot be scanned. We will have a look to the reachability of the pods, the security context, permission of the pods, network policies, and pod affinities. And at the end, we will be able to decorate and enrich our graph. As you can see, each pod, each edge, and each container has several attributes that define precisely its security context. The objective of this graph is to reconstruct attack path. So first, we will assign some dangerousness score to each component. So we have one first scale that will aggregate the different configuration analysis that we did to assign one score to each pod and node within the graph. Then we have a second scale, which is a bit more precise, where we can assign one single score for each tactic of the MITRE attack matrix. For example, for pod A, we can see whether the pod is vulnerable to the initial access tactics from the MITRE attack matrix, looking at the vulnerabilities, its accessibilities, whether it is easy to execute a program as root or to do privilege escalation. And we also look at lateral movement to other pods with the weight on the edges, and lateral movement to the host machine. And at the end, we try to reconstruct the shortest path within the graph to reconstruct possible attack path from an attacker point of view. So we basically consider the different entry doors in the configuration and reconstruct possible movement from an attacker to reach its final goal. So here is an example. We have a container with very critical vulnerabilities that allow remote code execution. It is related to a pod that is reachable from the outside, and pod A can execute other pods and can move to pod C which is a privileged pod and that access to the host network. So this is an example of a possible attack path. And in practice, we applied this methodology to many real-world configurations, downloading publicly available M charts, and 600 in total. And this is an example of the visualization of our tool. So it enables to have a quick view of the configuration and to compact many lines of codes for this deployment. So we can have a look to the different pods and different containers. We have a look to the vulnerabilities, to the root access, the permission, and the different connection between the components. And in this precise example, we can see that the pod is accessible from the outside. It contains two containers with opacity or with many vulnerabilities. It has a powerful service account where I can create new pods and new workloads. And there is no network policies at all. It can potentially move from other resources. So this helps in decision making for the administrator, and the objective at the end will be to minimize the weights on the nodes and the edge. So adding more fine-grained network policies, removing pod execution permission, adding role-based access control and new rules to the security context, or to remove unnecessary privilege or apply a more second profile to filter on the action of a possible attacker. So finally, Jacopo will present his contribution on Kubernetes cluster networking.
Yes, so we don't have much time. Let's try to be quick on this. I'll try to get it quick. We are at the last step of our supply chain. Our code is running in production, and what we can do here is to look for anomalies or intrusion detection systems or network monitoring, and that's what we're going to discuss now. The initial step of the initial idea is that with respect to every other sort of configuration that you can have as a code, the network-related configuration is special in the sense that those long YAML files do not represent the actual state of the system, especially when it comes to the port information. So the port information that you see in Kubernetes files is only for documentation purpose. And this, of course, can cause misconfigurations, both when you create an application, but mostly when you use a third-party app. Similarly, there is a lack of preventive security measures. What we've seen so far in the Kubernetes networking industry is that you try to create policies based on existing traffic. But what happens before that? Like if you don't have any traffic or if you don't know the application? Well, there is no solution for that. Here I'll show you an example of a misconfiguration. We have a pod named nginx, and this pod exposes port 80. Then we have a service that reflects this same pod and opens up a reverse, like a proxy. The service is basically a proxy, from port 80 to 8080, and then some random other port that was not written anywhere. And then last but not least, we have a network policy that again refers to the service and to the pod, and it opens up the nginx port, but also 6379 port. So the morality of the story is that there is no tool that can tell you, hey, there is something going wrong here. So what we decided to do was to create our own tooling to find out the actual state of the connections in the cluster. So we built a tool called KubeSond that is basically a distributed port scanner for Kubernetes. And the principle is pretty simple. Whenever you deploy a new application, we attach two probes. One called monitor that records the open ports, so basically netstat. And then it sends this information to a manager that collects the information from the YAML file, from the netstat output, and then decides which probes to send. so that we don't have a exhaustive search across the different cluster, but we know precisely which source and which destination to use. So by running this tool, we found some initial interesting problems. So first, many of the open ports that are in the containers, they do not match the clarity specifications. Then we see instances of connections of containers listening to all the interfaces, even when they should only listen to localhost, for instance. Then, as I got mentioned, lack of network policies and access control. Dynamic ports. So there is a quite interesting use of random or ephemeral ports in Kubernetes. And finally, access to public DNS and the internet. Just to show a little bit what we saw is that you are installing a WordPress and an Elasticsearch application. So you imagine that only the needed connections will be there, but in the end you end up with a complete graph and an access control mess. Like I would argue that it's not an easy task for a system administrator or a DevOps to understand the needed connections here. So after creating this tool, we want to actually to make it into use. So how can we find misconfigurations stemming from this documentation issues? So again, literature review, standards, white paper, research papers, best practices. This time we have seven different misconfiguration techniques that I'll show you. First, we have open port on container not declared. So we saw many instances where a container port is declared, but instead of one, there are multiple. So here, 8080 is not declared. Second type of misconfiguration happens when the container allocates dynamic ports. So on top of the declared 8080, we have ephemeral port open and nobody knows why. Then we have port declared is not open. So in this case, we declare multiple ports, but in the end, there is only one open. Then we have label collision, basically multiple pods belonging to different deployments share the same labels, creating race conditions. Then we have service issues. So what we saw before, basically services redirecting traffic from ports that do not exist or that are not declared. And then we have the well-known lack of network policies and container binding to the host network, where basically the container has the same access to the network as the host. Okay, now we have a list of possible misconfigurations. Let's see if they happen in practice once again. Once again, 6 datasets. 6 is just a coincidence. We selected different types of providers, including open source tools like Wikimedia or Bitnami, then cloud native tools like the Cloud Native Computing Foundation set of containers, Prometheus, and even some applications that are used in production by some European agencies. So we run our tool KubeSon and looked for these misconfigurations, and what we found is exactly that over 90% of the applications have at least one type of this misconfiguration. We're basically, we could say it's a documentation issue, but in practice, those type of issues can lead to more complex attacks. Then we see that the most type of misconfiguration that we see, apart from the lack of network policy, is the type M1, where a container opens up more ports than the ones that are declared. And this, for instance, makes it difficult for a system administrator to understand which policies to add in the system. So what we did is that we notified all of these providers, and as of today, more than 30 applications across the 6 datasets have fixed the misconfigurations, and we hope that this number will increase in the future. Now it's time for the takeaways and future work. So what we did today was a short overview of some aspects of the Kubernetes supply chain. We saw that container scanning is vulnerable to obfuscation attacks, and while the industry is overlooking this problem, we are raising some concerns about it and the potential challenges to vulnerability scanning. Then we saw a big picture of Kubernetes deployment. So it is important as a researcher, but also as a DevOps, to have a holistic view over the system to prioritize what to fix first in our cluster. And finally, we saw that configuration as code needs further research in the network realm, and that's because the declarative configuration doesn't always match the real state of the system. As a future work, we are thinking about other topics to somehow strengthen the supply chain. And we want to start by an attacker simulation, like simulating attacks and creating benchmarks for a secure supply chain. Then we're exploring the use of AI for improving SBOMs and vulnerability detection, especially in those corner cases where we are not sure about the content of a container image. And finally, another interesting research area is on self-healing networks. So networks then that can automatically respond to attacks or misconfigurations. That's it for our presentation. Thank you for listening, and we can answer a couple of questions, I guess.
Thank you.
First, thank you for your presentation. It's really interesting. Two questions. First, an easy one. I didn't see where your graph tool, the one that maps all the attack paths, I didn't see where it is. Is it accessible? Is it public? So that
the source code is not public yet, but I can easily make it accessible. So there is a publication that describes the tool, but I can also make the source code available. Okay. It's not yet.
Okay, great. I love that. Okay, and second question, I didn't really get what you mean by OS package obfuscation. Maybe it's just me not knowing things, but yeah.
So it's the package that you install with the package manager of your OS. For example, when you run apt update, apt install your software, there will be saved into one specific file. So here is an example for dpkg, for Debian. So all of the software that you install through the package manager of the OS will be registered into this file that will save the package and the version of each package. And if this file is deleted, for example, if you want to shrink the space of your image, you will not be able anymore to discover package installed via the OS package manager.
Thank you very much for your presentation. I have two questions also. You compare different scanning vulnerability solution. You talk about Orca. Is it your solution or Orca security?
Yes.
Well, Orca, it is our solution. We call it like this because it seemed like natural to say obfuscation-resistant container analysis. It's open source entirely, and it's made by us.
Okay. And the second one is for the ingress nightmare we have recently. Did you find a possibility to know if it's really accessible, like the pod network for the ingress and Nginx controller? I'm not clear. like the problem we have today is that the scanner vulnerability like yours find many CVEs and vulnerability, but when we try to see if it's indeed accessible from the internet, it's not. So it mitigated the risk, and I wanted to know if your tools can really try to access the pod, if it's accessible on the internet or not.
You refer to the last. Are you referring to the last Zoom?
Yes.
Okay. So yes, this tool is able to basically look first of all inside the cluster network. So basically, we could see if a pod is able to initiate access to the ingress nginx. So in that case, this tool would be able to protect you, kind of, against the latest ingress nginx vulnerability. And that's because our tool has the idea of preventive security. So we would scan the entire system before any actual connection would happen, while other tools, like tools that you would pay for and then use from cloud providers, they can tell you which traffic was happening inside your system, not the potential one. And that's, in our opinion, a big problem, because you would get notice of this ingress nginx vulnerability only after the vulnerability has happened. So that's not convenient for us.
Thank you very much. It's a really nice tool.
Thank
you. Last one.
Thanks for the presentation. My question is, did you analyze hardened images or not?
What exactly do you mean by hardened images?
It's images that follows hardened rules, like CIAs.
Ooh, okay. So we did not specifically analyze hardened images, and the reason is that we wanted to have a fair comparison schema. So we had to build our own dataset with something that we knew what was inside. So that basically is why we didn't. But at the end of the day, there shouldn't be much difference between what we did and hardened images, because what we found out is that many of the best practices for building container images, they actually cause obfuscation. So there should be a kind of a balance between a secure image and easy to scan image. And we have a lot of ideas on how we could do that. For instance, having a document on, or documenting how the image was built in the first place, so showing the intermediate steps inside the SBOM without the burden of having gigabytes and gigabytes of images. But this trade-off needs to be discussed a little bit more with the community.
Okay, thank you. We are a bit late, so we have to stop. Sorry. Thanks again. Céline? The next presentation is for Céline Mine from LAS NRS and Kistosi. Going to talk about an explainable by design ensemble learning system to detect unknown network attacks.
and to explain what happened on a network based on a set of detectors that can sometimes emit contradictory signals. So let's start with the context of this work. We will consider a corporate network supervised by a team of security analysts that will analyze the traffic to identify potential attacks. The problem is that there can be a huge volume of traffic daily, so the security analyst teams need a kind of tool to help them detect the attacks. This tool can be an IDS, an intrusion detection system, that will raise alarms every time it detects an attack. Those alarms can be either true alarms, which means that the IDS accurately detected an attack, or it can be a false alarm, which means the IDS raised an alarm when there was indeed legitimate traffic. Those IDS can be traditionally rule-based, like Snort or Suricata, but that supposes that we are able to exhaustively define all the attacks. And we want in our work to be able to identify new attacks. So we studied machine learning-based solutions. But among other things, there can be many algorithms in the literature. So we may want to consider multiple models to identify attacks. Let's see together a fictional case with 3 models: Model 1, Model 2, and Model 3. Traditionally, those models are used as black boxes. This means that we know the input flow and we know the output. Here, the output can be either benign or attack. The thing we notice here is that those models can provide different results for the same flow. For example, for the flow one, there is one model that say it's benign and 2 models that say it's an attack. So how can we know which result to trust? One thing we can do is to evaluate the accuracy, the global accuracy of the model on a dataset that we know. Here, the first model is the best one in terms of accuracy. Then the second model is the second best one in terms of accuracy. And the third model is the worst one in terms of global accuracy. Let's look at what really happened. If we look at the flow one, the first model is the only one that gave the good results. It was a benign flow, and the first one is the only one who detected the correct result. And that makes sense because it's the best one in terms of global accuracy. If we look at flow 2 and flow 3, it was an attack, and the 2 first models detected it as an attack. So that also makes sense. For the flow 4, all the models agreed on the good results, so there is no problem here. But what is interesting is the last case, is flow 5, where only the worst model in terms of global accuracy detected that it was an attack, so gave the correct result. So in our work, we want to be able to take into account the detection of the worst model in terms of global accuracy when it's relevant. We saw that machine learning models can make errors, and those errors can be hard to identify. So we want to work on how we can improve trust in the results provided by machine learning-based solutions. So we will first see how we can build a more reliable system to improve the detection performance, and how to explain the detections and present them to security analysts in the convincing way. I have talked about the context, and now we will see the approach. So one of the main topics of this presentation is explainability. And when we talk about explainability, there are 2 concepts. There is interpretability and explainability. And an interpretable model is a model whose logic can be understood, when the unexplainable model is something broader. It's a model that provides explanations. And we want to show the explanations to security analysts. And we don't expect security analysts to have any knowledge about machine learning. So we don't want to explain how the algorithm works. That's why we want to address explainability rather than interpretability. Then in the introduction, we saw that we are using multiple models to provide more accurate results. And this is an ensemble learning approach. And there are multiple ways to use multiple models. We can cite bagging. We can apply a SELM algorithm on different subset of data. We can talk about boosting, where we can try to improve a model sequentially. But in our introduction, we saw a case where models are doing the same task. So this is stacking. We want to combine multiple models that are doing the same thing, that are called base learners. And there are several ways of combining those models. We can either vote, or we can give weight to the models according to their performance. But in this case, we will not be able to address the case where the worst model in terms of performance is the only one to provide the good results. So we will explore a more sophisticated method called meta-learning. We will add another layer of machine learning on top of the base learner that will provide the final results. So we have talked about the introduction and the approach, and now we will see the system design. So this is a big picture of our system, and we will describe it component by component, and we will start by the network flow aggregation. So traditionally, traffic is described using network flows, and those flows can be described using hundreds of features. And we want to work on more concise representation. So we will, instead of analyzing network flows, we will aggregate those network flows using either the source IP address or the destination IP address, and so during a small time interval of 2 minutes. Those network flows, those aggregates, are described using a small set of features. We will analyze both aggregates by source and aggregates by destination, and those aggregates are each described by 9 simple features. Those features are statistical and they are simple to understand. For example, the number of flow or the number of forward packets. We saw how we represent the data. Now we will see how we analyze it. So we want to be able to detect new attacks. So we will consider unsupervised learning algorithm. And we will consider algorithms that are using very different mechanisms in order to detect more attacks. We will study isolation forest, local outlier factor, DB-scan, one-class SVM, unsupervised KNN, and COPOD. And we will study all of these algorithms on a data set, and we will select a subset of this model empirically. So we will see later in the evaluation part which subset we keep among all those algorithms. We will then identify a subset that detects the most attacks while minimizing false alarms. All those algorithms are able to compute a binary score. They can say if an aggregate is either benign or if it's abnormal. But what we want to do is to be able to score this anomaly. So for that, instead of giving all the 9 features to a same algorithm, we will consider all possible combinations of 2 features among the 9 features. And then we will apply a same unsupervised algorithm on all the subset of features. And by summing up those results, we will obtain an anomaly score. So those scores go from 0 for a completely normal aggregate to 36, which is the number of combination of 2 features among the 9 features. So this means that the algorithm weighs an anomaly on each subspace of features. So we analyzed aggregates on the same time interval using a combinations of models. Here we have 3 models, so they will each provide an anomaly score for each aggregate. And we wanted to represent visually those results. And for that, we assigned a color to each model. In this example, we have 3 models, so we assigned red for the first one, green for the second one, and blue for the third one. And we use the intensity of the color to translate the anomaly score. So if we look at the second model, the first pixel here is medium green. So that means that the first aggregate here is detected as moderately abnormal by the second model. If we look now at the second pixel is light green, so it means that model 2 raised an intense anomaly on the second aggregate here. And the 2 last pixels are black, so that means that according to model 2, those aggregates are completely normal. Now we wanted to have color-encoded segments that show the analysis of all those Bayes learners. So for that, we simply layered the monochromatic segments to obtain a color-encoded segment. And if we look at the first pixel here, it's gray. So that means that all the models agreed on the same result for the first aggregate. If we look at the purple pixel here, it means that for the third aggregate, model 1 and model 3 raised an anomaly, the red one and the blue one, but not the model 2. Then we put all those color-encoded segments that represent the analysis of the models during time interval together. We put them side by side, and we obtain the visual representation of anomalies. And the intuition behind this is that we want to be able to identify malicious sequences of events. Let's consider an example of a brute force attack, when an attacker may try to connect to authentify multiple times. It's an event that is not isolated, but rather repeated. So we want to be able to see in our representation those sequences of events. So we want a representation that highlights the sequences of alarms raised by the Bayes learners. So these representations aim to better identify attacks, so to improve the system accuracy, but it's also interesting in terms of explainability because it's a very concise representation that shows the traffic health to the network health to a security analyst in a very straightforward way. So this representation is something that we will show to security analysts to help them understanding alarms. So we have seen how we represent network anomalies, and we will now analyze them automatically using an attack pattern recognition module. And for that, we will use CNNs that are traditionally used in computer vision. But they are not reduced to pictures. They are analyzing a set of matrices. So our analysis is not restricted to 3 Bayes learners. We can use more. And we will use 2 CNNs to automatically detect attack patterns on those representations. And we will see in the evaluation that some attacks are easier to observe on aggregates by source, while others are more visible on aggregates by destination. So what we will do is that we will study both representations, and we will have a CNN that is analyzing the representations of aggregates by source, and a CNN that is analyzing the representation of aggregates by destination. And we will add another layer that will make and we will obtain a combined CNN that will give the final result, which is there an attack or not in the capture. So we have seen the whole system. We saw that we aggregate network flows by source IP or destination IP address during time intervals of 2 minutes. We analyze those aggregates using in this example, 3 machine learning models that compute monochromatic segments. We layered them to obtain a color-encoded segments, and we put them side by side to represent the anomalies in a larger time frame. Here it's 30 minutes. We analyze them using the attack pattern recognition module, which is a CNN, and it will say if there is an attack or not during the capture. Now we will see the experimental evaluation. We will validate each component on a dataset. And this dataset is the CSE CIC IDS 2018 dataset. So it's a project where a corporate network was implemented with 420 machines and 30 servers, as well as an attacking infrastructure. And this dataset consists on a capture of 10 days of network traffic where a variety of attacks was simulated. For example, brute force, denial of service, distributed denial of service. And what is interesting for us in this dataset is that it provides both the attack traffic and the legitimate traffic. So this dataset consists of 220 gigabytes of capture. We generated all the aggregates with the feature, and we obtained 10,000 aggregates. We then analyzed those aggregates using the algorithms that we saw previously, and we will see the results together. So we analyzed both the aggregates by source and by destination, and we evaluated the true positive rate and the false positive rate. So a good true positive rate is a true positive rate close to 1. It goes from 0 to 1, and we want something close to 1. And we analyze isolation forest, local outlier factor, THCon, one-class SVM, KNN, and copod. And what we see here is that individually the results are quite disappointing. The best model in terms of true positive rate is local outlier factor, and in both perspectives it is missing 10% of the attacks. So we want to combine those models to detect more attacks than that. And we define what we call the agreement zone and the disagreement zone. The agreement zone is the aggregates where all models agreed on the same result. And the disagreement zone is the aggregates where at least one model gave different results. And what we can see on both perspectives is that the disagreement zone is significant. So we will study it a bit deeper. So here we show the number of models that accurately detected an attack within the disagreement zone. And what is particularly interesting is in the destination here. So the second most frequent case, which is really significant, is where only one model accurately detected an attack among the set of models. So that is what we call a minority report. And if we look at the details of those minority reports, we can see that the model that provides most minority reports is local outlier factor. And that makes sense because it was the best model in terms of true positive rate. But it's not the only one that provides minority reports. There is also copod, KNN, and one-class SVM that had much lower true positive rate. So that means that by combining models, we will be able to detect more attacks. So what we did is that we studied all the combination of tree-based learner according to the true positive rate and the false positive rate, and we selected the ones that detected the most attacks while minimizing false alarms. So for source, the one we selected was local outlier factor, one-class SVM, and copod, and it was slightly different for destination. It was local outlier factor, KNN, and copod. So this was an empirical selection. If we go back to the detail, if we look at the source IP, we can see that the stacked model obtained by cumulating the alarms of all those based learners has a much higher TPR than local outlier factor. If we look at local outlier factor alone, we had a TPR of 0.89, and by cumulating the alarms of other models, we reach a TPR of 0.98. So this is much better. But the problem here is that as we are accumulating alarms, we have a much higher false positive rate. So now the next step will be to try to minimize this noise. So then we generated all the images representing the 30 minutes time frame, and we had in total 4,200 pairs of images. I will show you some example of these images. So this is an example of a denial of service. On the top we have the images representing aggregates by source, and on the bottom we have images representing aggregates by destination. On the left we have images generated by our unsupervised detectors, and on the right we have the labels, so what happens in reality. First we will see the labels. So in this picture, each line corresponds to a different IP address, and the columns correspond to consecutive time intervals. If we have a green pixel on the image, it means that there is a Benin aggregate in this IP during this time interval. And if we have a red pixel, it means that there is an attack. What we can see on both images is that there is a red line. So that means that the attacks consist on consecutive events, which makes sense because it's a denial of service, and it targets only one machine in the network. We are only studying internal IP addresses here, so the company machines. And now if we look on the left, we can see that we can distinguish on both images almost white line. So it means that in this case, the detectors managed to detect the attack because the white line is exactly matching the red line. If we look now at another case, which is a brute force attack, it's almost the same thing, except that we cannot see the attack on the aggregates by source. We can only see it on the aggregates by destination. And this means that the victim never initiated a network flow towards the attacker. So that makes sense. But we can only see the attack on this perspective, and it's accurately detected by the multiple detectors. And now I will show you another case, which is a data exfiltration. So in this case, we can only see the attack on the aggregates by source and not on the aggregates by destination. And what is interesting here is that there are multiple machines that are emitting traffic towards the outside. And what we can see here is that we don't have a white block or white lines like on the other perspective, but we have a kind of interesting shade that we don't see anywhere else on the picture. So this is a pattern that we want to analyze. And why do we have this dark shade? That makes sense because it's a data exfiltration, it's a stealth attack. It's an attack where the attacker wants to remain undetected as long as possible. So that can explain why our detectors struggle to detect anomalies on this traffic. I have shown you an example of visual representations, and I will evaluate the attack pattern recognition module. So we evaluated the F-score of the combined CNN, which is a score that goes from 0 to 1 for a perfect model. and we obtained a F-score of 0.99, which is good. If we look now at the confusion matrix, we can see that there is one false negative, which means an attack that was not detected, and 3 false positive. Let's look at this false negative. So this is a visual representation of the false negative. And what we can see here is that there is only one red pixel, which means that there was only one aggregate corresponding on the attack, and it was only on the destination perspective. So we can understand why our CNN didn't detect this attack, because it's hard to see. It's this pixel. It's very hard to see that there is an attack on this capture. But we refer to the documentation, and we observe that this pixel corresponded to the very end of an attack. So here is the current time. This is the past. So this means that the attack was detected before. So in practice, this false negative has no impact. So to conclude, we evaluated our system on the CIC dataset. We generated all those aggregates, we generated all the visual representations, and we obtained a system that missed no attack in practice. And that leads to the main message of this presentation, which is that explainability improves accuracy. Usually we talk about compromise between explainability and accuracy. And that we wanted to show is that by analyzing the data step by step, which is what guided the design of our system, we managed to improve the detection performance. So we improve the detection performance through the understanding of the behavior of the components. We analyzed them individually and we saw how they behave. And our explanations not only allowed to improve the system accuracy, but also allow to involve security analysts in the detection of potential system errors. We observed that the only false negative raised by the system corresponded to the end of an attack. So by examining this visual representation, a security analyst would be able to spot this attack. So let's conclude. We developed an ensemble-based method that significantly improves the performance of the unsupervised base learners, and we decompose the system analysis by providing an attack report including pairs of anomalous features and visual representations showing attack patterns. So these elements enable security analysts to make both efficient and informed decisions. So in the future, this system will be evaluated on a larger and better documented dataset to enable error investigation. And it will also be tested on real-world data because this work is intended to be integrated into Custos' NDR solution. Thank you for your attention.
Thank you, Céline. First question.
Hi, thanks for the presentation. First question, how long does it take to detect an attack?
We didn't try to evaluate the runtime, but I measured the time for the training and detection. So when we tuned the CNN, etc., and it took 2 days to evaluate the 10 days. So in practice, it will be much shorter than that, and it's quite reasonable to enable security analysts to react on time.
Okay, thanks.
Hi, thank you for the presentation. It was very interesting. I was wondering what motivated the choice of using a set of colors in matrices for the representation and explainability of this research?
So the question is why we decided to use colors?
Yes. Or what's the main? Sorry. Yes. What's the reason, or what motivated the choice of using this way of representation?
So basically, it happened when we tried to evaluate the base learners. So we have the true positive rate and the false positive rate, and we wanted to try to understand how this behaves. Because when we see only the true positive rate and false positive rate, it's very hard to distinguish the false alarms and the true attacks. So we wanted to introduce representations that allow us to see a meaning to this. And we had this idea of having a kind of heat maps that shows what is important in the image, where are the anomalies, if they are, is it targeting the same address, is it doing the same time? And what we saw is that it was interesting to have 3 models, because 4 models, it means that we had 8 matrices to analyze, and this was a lot. We are doing like GPU analysis for the CNN, and we were exploding the rhythm of the GPU. So 3 was enough, and we managed to detect the attacks using those trees. So that's why we had this idea of using those colors.
Okay, thank you.
Okay. Last question, because we are late. Last one.
Thanks for the presentation. I'm not sure to understand one thing about your brute force scenario, because you say only the destination IP aggregation show attack red dots, but not the source IP. And I don't understand why. Is it because the brute force was distributed over many sources? Because when some attacker made a brute force, it's from an IP to another. So in my first thing, we can see the attack by destination IP and by source IP.
So it's aggregates by network flows, and the direction of the network flows is given by the first packet. So it doesn't mean that the victim is not responding, it means that it didn't initiate. Does it answer your question?
Well, we'll discuss about that at the break, I think.
Okay.
Okay, so we have to switch. Thank you. Thank you, Céline, again. The last presentation before the break is a short presentation. Is a short presentation from Manuel Poisson, from Amosis et Centrale Supélec. CVO representation to build attack position graph.
My name is Manuel Poisson, and I'm very happy to be here to present some of my work about CV representations to build attack positions graphs. And this is a joint work with Valérie Viet-Riemtong and Gilles Guette from the Pirate research team related to Central Supélec and INRIA, and also Frédéric Guilry and Damien Crémieux working with the company Amosis. So basically, to go back to the basics, the NIST defines a vulnerability as a weakness in an information system that could be exploited or triggered by a threat source. And when you're performing a security audit, you can use a scanner like Nessus. Here you have at the right of the slide a screenshot of Nessus scanner that will unveil some vulnerabilities, and it will say the vulnerability with this identifier is present on this machine. And you have, for instance, an identifier of vulnerability can be a CVE 2021-38648, which is, so now you know there is a vulnerability with an identifier, but what do you do with this? What is the real impact? To do so, you can look at different information sources in the National Vulnerability Database, or NVD. You can have a short textual description of the vulnerability, which is in natural language. You can look at the CVSS, Common Vulnerability Scoring System, which will help you to capture the severity of the vulnerability based on different components in the CVSS vector, like the attack vector, which can be local, or the privilege required, which can be low or also medium or high, for instance. You can have a higher level, more abstract view of the CVE by looking at the weakness, the CWE, and then you can follow MITRE links to know the related attack pattern, CAPEC, the attack technique, or the attack tactic. And finally, you can learn a lot about a CVE by looking at the related exploits, and you can sometimes find public exploits on Metasploit or ExploitDB, and the exploit is the piece of code that will trigger the vulnerability and exploit it. As an illustration, we can talk about the vulnerability known as Log4j shell that is identified by CVE 2021-4428, which is an injection vulnerability allowing a remote code execution, meaning that if the attacker can exploit this, he will have full access to the system from anywhere in the world. And in this context, we asked ourselves, how can an attacker exploit CVEs in a whole attack scenario? To answer this question, we based our work on a previous proposed model with an attack scenario, which can be represented as a graph of attack positions. And here, the nodes of the graph are attack positions with one account being compromised on a given machine. And then you can have lateral movements, so taking control of a new machine, but keeping the same user. You can gather some information to increase your knowledge about the information system, or you can have a vertical movement, like taking control of a new user, but staying on the same machine. And we ask ourselves, how can we use CVEs to build such graphs? We think that CVEs only are not enough, and you need to have a description of the exploits to know also the location of the attacker before the execution, and the required privileges for the attacker to exploit the vulnerability, the location of the attacker after the execution. And also we think that after reading the description of the exploits, you're still missing some of the results, the benefit of the exploitation. And we proposed the KPG format to represent CVEs. So KPG being an acronym meaning from CVE to attack positions graph. And this format will represent a pair of a CVE and its related exploits. And if you represent the CVE and the exploit in this format, you will be able to more easily build attack positions graph based on a list of CVE. And the main new information it brings are the constraints between the source and destination machines, the source user, the destination user, and finally the constraints linking these two users. So now that we know how we want to populate, how we want to represent the CVE and the exploit, how do we populate this KG format? Some fields can be easily computed by statically reading available information, like the CVE field, which is the identifier of the vulnerability, and this is our starting point. The exploit can be found, for instance, on Metasploit using the search CVE command in Metasploit console. And here at the bottom of the slide, you have a screenshot of what Metasploit console look like. And finally, Vun class will represent the type of vulnerable asset, which can be, for instance, the operating system or the software. And this is simply the third field in the CPE. However, for the remaining fields, you need to actually exploit the CVE to know what are the different constraints on the source and destination machine and users. And since you need to exploit the CVE, the requirement is an environment that will be vulnerable to the CVE you're analyzing. To do so, you can use Decret, which is a tool that is able to deploy a Docker container vulnerable to a given CVE. Concerning the field machine constraints, we will try to exploit the vulnerability from the least restricting environment to the most restricting one. And we will find what are the least constraints required to exploit the vulnerability. So at first, we take two different machines, and we try that are not related, and we try to exploit the vulnerability that is located in one of the machines. If the exploitation succeeds, we know that there is no constraint between source and destination machines, and they can be different. If it doesn't work in the first case, we try the second one, where we still keep two different machines. However, we can put them in the same Windows domain, for instance, or in an adjacent network. And if it succeeds, we know that the machine can be different, but they must be, for instance, in the same Windows domain. And finally, the most restricting case is when source and destination machine must be the same. So exploitation remotely is not possible. Concerning source and destination users and the constraints between these two, the principle is the same. You will try to exploit the vulnerability from different users with different level of rights, and you will look at which user was reached after a successful exploitation. So if we go back to our example, we can imagine an information system with two machines, and the vulnerability scanner raised 3 vulnerabilities. We can represent the vulnerability with a KG format, and it will tell us that the first CVE, which is located on M0, can be exploited from a remote machine, and there is no constraint between source and destination machine. And you can exploit it from any user to gain access to a machine local account. The second CVE is still on M0. You need to exploit it from the same machine as the vulnerable machine. And you need to have a machine local account to exploit it, which will give you access to a system or root account. And finally, the third CVE, located on machine M1, there is no constraint between source and destination machine. However, you need to have access to an application account, and you will be able to gain access to a machine local account after a successful exploitation. If we imagine also the user's accounts which could exist in such information system. We can have the user utomcat, which is a purely local user on M0, where Apache log4j 2.0 is executed, making the machine vulnerable to CVE1. We can imagine the user root existing on M0, and also the user ubigbucket, which is a user account of a Bitbucket repository available on an application server and data center, which is executed on machine M1. And with this knowledge, we can derive the following attack graph, where an attacker from any machine and using any user account, he will be able to exploit the first CVE and gain access to user utomcat. From here, he can exploit the second CVE because he has access to machine M1 and he has a local account. He can access the user root using the second CVE. And here, he can explore, discover the accounts of ubigbucket. And there, he will be able to exploit the third CVE and gain access to machine M1, which can be his final target. To conclude, we asked ourselves how can we reconstruct a complex scenario from a list of CVEs with a few information about the user's account. And our main claim is that CVE are not enough on their own. We need to describe them more precisely, and in particular, understand what the CVE exploit can do. To do so, we propose the KG format to describe the attacker propagation through the execution of an exploit. And this format can be populated by experimenting with the execution of an exploit in a vulnerable environment. And as a future work, we plan to automate this scenario reconstruction in a larger scale environment. Also, as a very short-term future work, my plan is to answer your questions if you have some. So thank you very much for your attention.
Thank you, Emmanuel. Again, we have two questions. It's okay.
Thanks for your presentation. Here. Just one question about your the prerequisite of being in the same domain and same LDAP. What is the difference for you? Because mainly Windows domain is LDAP with little garbage around.
Yes, so concerning this, some fields are obviously incompatible. For example, you cannot have a machine constraint that be same and different at the same time. About the difference between Windows domain and same LDAP, I mean, sometimes you may have, by domain I would mean Active Directory domain, and sometimes you may have extra constraints that only exist in Active Directory.
Hello, thank you for the presentation. Your CapMG additional information must be filled in by who? The analyst of a given vulnerable system, or by the provider of the CVE?
Well, ideally, I think it will be very useful if it's provided, like published jointly with the CVE and the identifier. But I think some analysts could, if you are an analyst, the security audit reveals that some CVE ID are available in the information system. You could try to populate the KFG format for these CVE IDs, and then really know what is the impact of the CVE and how they could be chained together.
for your understanding, it's realistic to say that CV writers will add this kind of information for tens of thousands of CVs each year?
Well, at least CV writers do not write 10,000 CVE. Each CV analyst, each analyst does not write 10,000 CVs. All CVs are written by different people, but at least we provide propose a way to populate the format easily.
Thank you.
Okay, I'm sorry we have to stop here because we are late. So thanks again. And if you have questions, you can ask during the break. So we have 20-minute break, please. So we start at 11:25. Thank you. PF is here. Gabin, can you come and see me, please?
La cybersécurité aujourd'hui, c'est l'enjeu numéro 1 des dirigeants. Et chez iTrust, on s'est donné pour objectif de protéger les actifs stratégiques des entreprises. Et par-delà ça, protéger le citoyen européen, sa vie privée, son emploi, sa démocratie, sa souveraineté. iTrust, c'est un des premiers pure players cybersécurité français. 1200 clients, dont 6 sociétés du CAC 40 nous font confiance.
Par exemple, nous accompagnons quotidiennement 60 structures de santé et organismes publics. Et nous protégeons une centaine de clients ETI et grands comptes. Et ils nous restent fidèles.
iTrust accompagne le client pour co-construire avec lui sa sécurité. C'est une équipe qui est dynamique et qui propose des outils innovants.
C'est l'agilité, le professionnalisme des collaborateurs avec qui on travaille.
Nous sommes certifiés par l'ANSSI, l'État français, la CNIL, le ministère des Armées et surtout certifiés PASI.
Notre grande fierté chez iTrust, c'est d'avoir déjoué 100% des attaques sur l'intégralité du parc client ces 5 dernières années.
Au sein du centre de supervision, nous traitons chaque jour 4000 alertes qui nous permettent de déjouer environ 80 attaques grâce à la solution Rebellium. Rebellium, c'est une solution souveraine qui est développée en interne depuis 2017 et qui inclut des éléments d'intelligence artificielle. La cybersécurité, c'est avant tout de la prévention. Nous sommes à l'origine d'une des premières Red Teams d'Europe.
Alors nous, on est ce qu'on peut appeler des hackers éthiques. On réalise plus de 150 audits par an afin d'identifier les vulnérabilités et permettre aux clients de les corriger.
Et la prévention, c'est aussi l'automatisation de la détection des menaces par notre logiciel iCare.
Élargir notre offre, c'est notre enjeu aujourd'hui. iTrust, c'est aussi des solutions de darknet, de threat intelligence et bien d'autres. Et Free peut nous aider à être leader sur ces marchés.
Avec Free, nous avons les mêmes valeurs d'innovation, d'ambition et de valorisation de nos collaborateurs. Et nous sommes très fiers d'afficher un taux de turnover de seulement 3%.
L'esprit de Free et d'iTrust, c'est de démocratiser l'accès à des solutions qui étaient dédiées à des grands groupes pour les rendre accessibles à tous. La confiance que nous accorde Free fait de nous le centre d'excellence cyber du groupe. Une confiance que nous devons à tous nos clients depuis 2007.
Ouais.
Action.
Bonjour, je suis Dora Sadan, je suis diplômée d'un master en spécialisation sécurité de l'informatique à l'ESGI et j'ai décidé d'intégrer le groupe Soprasteria en tant qu'alternante en janvier 2022. Cette expérience en alternance m'a permis d'obtenir des compétences fonctionnelles en plus des compétences techniques que j'ai apprises lors de mon cursus en école d'informatique. J'ai décidé donc de poursuivre cette aventure au sein du groupe Soprasteria dans laquelle j'ai commencé à partir de septembre 2023 en tant que consultante junior et j'ai pu évoluer très rapidement au poste de responsable de sécurité opérationnelle. J'ai décidé de signer mon premier CDI chez Soprasteria, surtout pour ses qualités humaines. En effet, il y a beaucoup de flexibilité dans un premier temps sur le télétravail, ce qui est plutôt pas négligeable. Il y a également une proximité avec les collaborateurs qui est très riche, qui permet aussi une entraide entre collaborateurs et aussi une ambiance de travail et des locaux qui sont très agréables pour travailler. En tant que responsable de sécurité opérationnelle au sein du groupe Soprasteria, mes journées sont très enrichissantes et stimulantes. Au quotidien, j'accompagne en fait des équipes techniques qui travaillent pour le client sur toute la cyber-résilience et donc couvrent plusieurs périmètres que je supervise, la gestion des vulnérabilités, de l'obsolescence ou encore la gestion du patching. Ces thématiques permettent en fait de répondre à la gouvernance cyber des clients et c'est quelque chose de très stimulant pour ma part puisque j'ai toujours voulu m'orienter dans un aspect de chefferie de projet dans la cybersécurité. C'est ce que j'ai pu faire au cours de ces derniers mois et grâce à cela, aujourd'hui, je travaille quotidiennement avec les équipes internationales de Soprasteria, Inde, avec lesquelles donc, je collabore et je dirige les activités pour mes clients. Je me rends d'ailleurs chez eux très prochainement afin d'échanger sur ces sujets. Un de mes meilleurs souvenirs au sein du groupe Soprasteria a été sans hésiter un séminaire qui a été organisé l'année dernière dans un grand palais à Opéra. Occasion pour moi de rencontrer les équipes cloud avec donc, nos équipes cyber. Ça a permis d'interagir avec ces équipes, de renforcer l'esprit d'équipe également et de partager nos expériences. Ce séminaire m'a permis de me sentir valorisée et de vraiment me rendre compte de mon importance et de mon réel sentiment d'appartenance au groupe Soprasteria. Un clap ? Merci.
Dans un monde qui ne cesse d'accélérer, toujours plus numérique, encore plus connecté, les menaces accélèrent elles aussi, de plus en plus complexes, plus globales et organisées que jamais. En un seul clic, tout peut s'arrêter. Orange Cyberdéfense est là. Nos 30 années d'expertise forgées au sein d'Orange nous ont hissés au rang de leader européen de la cybersécurité. Nous accompagnons tout type d'organisation, grandes entreprises, PME, usines, administrations, entrepreneurs et particuliers. Notre ancrage est européen, notre présence est mondiale et nous agissons localement. Avec nos cybercentres basés dans 22 pays, nous opérons dans le monde entier. Nos experts pluridisciplinaires protègent toutes vos expériences digitales parce que la cybersécurité est avant tout une aventure humaine. Nos cyber-experts font toute la différence en étant toujours plus créatifs et en se projetant toujours plus loin. Cet esprit hacker associé à nos services et à notre expertise technique, enrichi par l'IA, alimente une connaissance de la menace unique, renforçant notre approche end-to-end. Nous construisons ainsi une société numérique plus sûre. Nous sommes Orange Cyberdéfense.
La cybersécurité aujourd'hui, c'est l'enjeu numéro 1 des dirigeants. Et chez iTrust, on s'est donné pour objectif de protéger les actifs stratégiques des entreprises. Et par-delà ça, protéger le citoyen européen, sa vie privée, son emploi, sa démocratie, sa souveraineté. iTrust, c'est un des premiers pure players cybersécurité français. 1200 clients, dont 6 sociétés du CAC 40 nous font confiance.
Par exemple, nous accompagnons quotidiennement 60 structures de santé et organismes publics. Et nous protégeons une centaine de clients ETI et grands comptes. Et ils nous restent fidèles.
iTrust accompagne le client pour co-construire avec lui sa sécurité. C'est une équipe qui est dynamique et qui propose des outils innovants.
C'est l'agilité, le professionnalisme des collaborateurs avec qui on travaille.
Nous sommes certifiés par l'ANSSI, l'État français, la CNIL, le ministère des Armées et surtout certifiés PASI.
Notre grande fierté chez iTrust, c'est d'avoir déjoué 100% des attaques sur l'intégralité du parc client ces 5 dernières années.
Au sein du centre de supervision, nous traitons chaque jour 4000 alertes qui nous permettent de déjouer environ 80 attaques grâce à la solution Rebellium. Rebellium, c'est une solution souveraine qui est développée en interne depuis 2017 et qui inclut des éléments d'intelligence artificielle.
La cybersécurité, c'est avant tout de la prévention. Nous sommes à l'origine d'une des premières Red Team d'Europe.
Alors nous, on est ce qu'on peut appeler des hackers éthiques. On réalise plus de 150 audits par an afin d'identifier les vulnérabilités et permettre aux clients de les corriger.
Et la prévention, c'est aussi l'automatisation de la détection des menaces par notre logiciel hacker.
Élargir notre offre, c'est notre enjeu aujourd'hui. iTrust, c'est aussi des solutions de darknet, de threat intelligence et bien d'autres. Et Free peut nous aider à être leader sur ces marchés.
Avec Free, nous avons les mêmes valeurs d'innovation, d'ambition et de valorisation de nos collaborateurs. Et nous sommes très fiers d'afficher un taux de turnover de seulement 3%.
L'esprit de Free et d'iTrust, c'est de démocratiser l'accès à des solutions qui étaient dédiées à des grands groupes pour les rendre accessibles à tous. La confiance que nous accorde Free fait de nous le centre d'excellence cyber du groupe. Une confiance que nous devons à tous nos clients depuis 2007.
Ouais.
Bon, de toute façon, je peux lancer PF, il n'y a pas de souci. Oui, je peux lancer, ouais. Okay, so we're going to start the session with a presentation from Pierre-François Jiménez, from INRIA, from Bretagne. So the title of this talk is for Chronicles, Synthetic Network Flow Generation through Pattern Set Mining. So Pierre-François, the floor is yours.
Thank you very much, Vincent. Hello, everyone. So yes, I am Pierre-François Jiménez, researcher at INRIA from Rennes. So I'm here because it's sunny. I'm going to present you a joint work with CISPA and INRIA. So it's a work done by Yosha Kuppers, Adrien Schoen. Adrien, if you're here online, hello. And Grégory Blanc and myself. So my work as a researcher aims to protect information systems, and how can we do it? By preventing attack, detecting it, and reacting to it. I mostly work on detection with IDS, and we have two main sources of information to detect attacks: system logs and network communication. And if you ask a researcher what is the main issue with IDS today, we can give you a few answers. Typically, our APT are very difficult because they are very stealthy. They can be weeks behind, between two steps of the attack. There is a lot of false positive. We want to try to mitigate them. It was Céline talked about that earlier today. But there is a lesser known issue is that we need some good quality data in order to perform this protection. More exactly, we need data for two main issues. First, we want to evaluate the security measures. We want to know how effective they are in reality. And also, we need data for machine learning and cybersecurity. And currently, researchers, to evaluate their methods, they use public datasets. They use public datasets that do not contain any actual data, because we cannot just probe one network and take all the data from it for confidentiality and privacy reasons. So the public datasets we use are in fact from testbed. So there is no real users, it's just some scripts and so on. Also, they suffer from mislabeling, there's some misconfiguration and so on. So the data is quite poor quality. And the issue is that even a detector that works very well on this data, we cannot be confident that it will work in real life. And that's a big issue. There's several ways to deal with that. And the main the new I will take is to use AI to generate synthetic network data. So as you know, network data is mostly, it's made of packets, like this one. And typically, packets are regrouped in flows, in conversation. And most of the time, to detect attacks, we do not look into each individual packets, but we look into flow statistics, like net flows. So in this work, we want to generate net flows. What does it look like? For example, here, on the bottom, there is a timestamp. It's between source IP .23 and destination IP 87. It's on port 443 on TCP. There is 33 forward packet, 41 backward packet, and so on. So we want to generate this kind of statistics. And then you can just tell me, OK, we have LLMs. LLMs can generate anything, so problem done. Thank you, bye. But of course, it doesn't work very well. We tried a lot of methods, deep learning methods, variational autoencoder, GAN, LLMs, but they have some significant drawback. Typically, a large portion of the data we generate just do not comply with network protocols. For example, IP come in two flavors, 4 and 6. If you generate a packet for IP5, it doesn't work. And this is the kind of issue that can happen with these methods. Another issue is that we want to generate a large diversity of behavior because our goal is to assess the quality of intrusion detection systems. So we want to have a lot of edge cases to test them. If we generate always the same examples, then we won't challenge the IDS. Besides, these models are not explainable, so when the generation is not good, it's not easy to know why. And more generally, there are some dependencies that are not well replicated. We can differentiate two kinds of dependencies. Dependencies inside the flow, for example, the port depends on the destination IP, the number of packets depends on the application protocol, and also interflow packet dependency, sorry. For example, before an HTTP, you can sometimes see a DNS request. When I open my email with some IMAP, if there is some images, my webmail can request some HTTP request to get the images, and so on. So we propose a new method to generate synthetic network data named Flow Chronicle that works by using a pattern language to capture these intraflow and interflow dependencies, and then to generate data with these patterns. And these patterns, by design, are interpretable and auditable. So how does it work? First, what is a pattern? By pattern, I just mean a frequently occurring substructure in data. So it's a very broad definition, so we need to define more precisely for our problem what is a pattern. This is what is called the pattern language. So once this pattern language is defined, we'll try to find a small set of patterns that best describe the data. And to know how well patterns describe the data, we'll try to look how well the patterns that can compress the data. So what do the patterns look like? There is two parts. On the left, you can see a table, which we call the partial flows, and on the right, you can see a Bayesian network, which is a statistical model. And in this table on the left, you have three kinds of colors. Yellow means that the value is fixed, it will always be these values. The blue means that it's a randomly selected value, depending on the Bayesian network. And green means that the variable is reused. So for example, here, on the left we have 2 lines, so it means there is 2 different flows. The first one is contacting A.A.8.8 on port 53, so DNS. So this is fixed because it's yellow. And the source IP is random. I didn't put the distribution on the top right on the Belgian network, but it's not just any random IP address. It's more like IP A with 80% of chance, IP B with 15% of chance, and IP C with 5% of chance, for example. And then we have a second flow, second line, and the source IP is the same as the source IP of the first flow. And it's contacting a destination IP that is random, but we can see on the right, on the Belgian network, there's an arrow from the source IP of flow 1 to the destination IP of flow 2. It means that the destination IP of flow 2 depends on the value of destination source IP of flow 1. And here the port is fixed. So our goal is to learn, to mine this kind of patterns automatically from the data. How do we do that? We generate some pattern candidates, and then we test them, and if they are useful, we keep them, otherwise we throw them out. To generate new pattern, we can just add a new line to an existing pattern, or we can also merge 2 existing patterns into one. So the algorithm is quite simple. We start with an empty pattern. We generate some new pattern candidates. We try to compress the dataset with these patterns. If we can compress it more with these patterns, we can keep it. I said that we need to compress the dataset. So first we need to cover the dataset to find these patterns in the dataset. How does it look like? For example, here on the right is the dataset, and on the left it's a set of candidates. There is 3 patterns here, gray, blue, and green. And on the right, we try to find where these patterns are matched. You can see here that the patterns can interleave. They don't have to be consecutive because, of course, when we measure some network traffic, there is always some traffic that's not sequentially sorted. So we have to be able to detect this interleaved pattern. And then there is some math to select what is a good model. It's quite scary, to be honest, but it's just really a compression. How many bits can I compress the dataset using this pattern? When we identify these patterns, we can generate some data. It's quite straightforward. We select pattern from the model we learned. We generate the first timestamp, and then the delay between each flows, and we fill the values. If the value is fixed, is yellow, we can just put it directly. If it's blue, we can sample it randomly. And if it's green, we just reuse a previous value. Okay, but does it work? That's a good question. I hope so, otherwise I would not be here today. But first, what does it mean to work correctly for a generative method? Because, okay, if I do some AI to detect what is a cat, what is a dog, I can easily evaluate how good it is. I can just say, okay, here is a pile of images, and I will just count how many errors you do. The less errors, the better you are. But here we want to generate data, so we have no ground truth. We don't know what should be generated. So we have to be a bit clever about it. And first, there is no standard metrics for that. And in most articles, they use 1 or 2 metrics, but they do not encompass the overall quality we need. And in fact, we want to evaluate 4 different criteria. We want the data to be realistic. It means that the data could actually exist. We want some diversity, so we want to generate a wide array of different behavior. We want some novelty. We want some new data that was not present in the original data. And we want some compliance. We want the packets, the data to be actually usable in a real network. Some of you may say that, oh, but you do not consider privacy. And indeed, I do not consider privacy. It's already a a bit of work to make all that happen, and for now we did not consider this this criteria. Since we learn from public datasets, we assume that there is nothing personal in this dataset. So when we generate some data, we cannot spontaneously create new personal information. So right now we cannot generate, the data generated cannot have privacy issue. But for later it could be an issue. So how do we evaluate our method? We use a dataset called CIDDS001. And we use 1 week of data to train the model. And we ask each model to generate another week of data. So we compare our methods with other methods, Bayesian networks, variational autoencoders, GAN, and transformers. And then there is this cheaty little guy at the end, the reference. We took actual data from a dataset. And it is a way to simulate the best possible generation. Because ideally, I want to generate data that could have been really measured. So this reference is just a way to see how far we are from the ideal version. I won't bother you with all the details. This is for the non-temporal evaluation. We just compare each flow independently. We have many different methods. And on the top, you can see the different metrics we use. But overall, our methods rank the best along these. And then we want also to evaluate the temporal dependencies. To do that, we split the study between numerical and categorical features. For numerical features, we use the autocorrelation, and we want to have an autocorrelation of features that is similar between the training data and the generated data. So here, the difference should lower is better. So we have the second one, and for this experiment, it's very, very low compared to the other one. And for assessing the categorical features, what we do is that we learn an LSTM model, so a model that tries to predict the next item in the sequence, and we training on the actual data, one model on actual data, and one model on synthetic data. I want to see how well they can work on the actual data. The closer we are, it means that our data was good enough to learn an actually good model. For this problem, we are a bit less good. We can see that sometimes we are not the best possible model, but overall we are quite happy about the results. I want to take a few words to say what we did beyond Flow Chronicle, because right now we can generate some network flow records, but our actual goal is to generate some packets afterwards. And the question is, how do we generate packets from this kind of data? In fact, we do it with an intermediary steps where we generate not directly the packets, but some tuples with the direction of the packet, the TCP flags, the size of the payload, and the time between the last packets. So for each flow, we generate a sequence of these headers. Intuitively, we would like to use the actual automata of the protocols, but most of the time we don't have access to it. So we proposed a new method to learn this finite state automata from passively, from observations. In fact, we tried to use some algorithm from the state of the art to learn automata, but we did not deal with noise correctly. So as long as there is a bit of noise in your data, for example, oh, I didn't see one packet because I know it took another path, or maybe two packets were swapped because they arrived almost at the same time at the probe. This algorithm would just produce automata that will be way too complex. So we proposed a new method called TADAM to learn an automaton from observations that is robust to noise. And in a few modes, we are indeed more robust to noise. We learn smaller models, and we have better performances on the real-world classification task. We skip that. So for example, for the Kerberos protocol, on the left is a state of the art. We give it some example of Kerberos communication, and it produces this state automata. And on the right, we have our methods that do not deal with with some issue with on the left because of noise. So it's quite easier to use and to assess. These methods output the tuples I presented earlier with the direction of the packet, the flag, the payload, and the interval time. And then you want to create the actual full packets. So from this data, the tuples, it's quite easy to reconstruct the rest of the header because, okay, checksum, we know the algorithm, and so on. For window size, it actually depends on the OS and version of the OS, but you can write the heuristics. And then there's a big issue with the payload, and right now we just replay some previously seen payload. It's a difficult problem we won't tackle today. And so these three tools together created Fusser, which can create pickup files and also can be used for network injection. For example, it was used for the Brest CTF, the biggest in-person CTF in France, where it was generated for for a challenge with seven computers, and there was some fake traffic that was generated by these models and then played on the network. So the attacker can have some false lead and can believe that it's an actual systems. It's also used for Oninet when you want attacker to believe that this is an actually used information system and just not some empty computers. So in conclusion, we need good quality data to assess our methods. And right now, we do not have this good quality data. There's several ways to improve this issue, and one way is to use generative AI to generate data. With Flow Chronicle, we propose a new method based on pattern mining to generate this data, and that maintains both quality and temporal dependencies, and it outperforms other generative models. Besides, the patterns are auditable, so we can have experts that verify if the patterns actually make sense or if it's just some artifact from the dataset. And then we'd like to go into the next step, which is not only generate pickup, but also system logs and have some joint, consistent data. Thank you very much.
Thank you, Pep. Time for questions.
Any questions?
I have one.
Could your model be used to create fake data that includes attacks? I assume that the model currently generates normal benign traffic. Could it be used to generate, for instance, data sets to then detect those attacks?
Yeah, good catch. I didn't talk about attacks at all, and indeed, we did not use these models to create attack. We believe that attacks are carefully crafted packets. So with these methods, we try to wiggle around a bit to have some different packets, and I think it will destroy the efficacy of attacks. So right now I'm working on a project when we try to take actual attacks and transfer them into data sets. So we are sure they still work.
I like the overview you made about your tool, but there is something I didn't get, so I would like you to elaborate a little bit. It's how you generate the correlation, the intra-flow correlation. So you have been combining a model of losses with LSTM resources and the state machine of the protocols. How do you combine all that to generate the correlation in the flow?
So when I talk about LSTM, I got a bit fast about it. It's just a way to evaluate our methods. So we have some generated data from any methods, and we fit an LSTM on a feature, on a categorical feature, to see if it could be useful, it can correctly identify a sequence of these features taken from actual data. So it's not part of the generation process. It's only for evaluation.
Other question? No? Okay.
Well, that's it.
Okay. So thank you. Thanks a lot, Dave.
Thank you.
We have next presentation last before the break.
The best part of the day.
Yeah. Presentation is from Gabin Noblet, from la CNRS and KIST aussi. The title of this presentation is Network Traffic Generation. This is the same topic as PF, but the method is different. Network traffic generation via an optimized generative AI. It's okay?
All right, yes. So hello everyone. So I'm here to present NetCliffizer, another way to generate realistic network traffic using generative AI. So I'm working at Custocy here in Toulouse. So we are basically leveraging AI for network intrusion detections to help analysts on the investigation. So I already have a good introduction to this subject, so you understand that machine learning tools for network analysis needs a lot of data and needs labeled realistic data sets, either for the development of network intrusion detection solutions or the evaluation and benchmarking of those solutions. And the key bottlenecks of this approach are the privacy, because for company data, we cannot extract data easily from companies. We cannot really deploy realistic complex architectures without introducing too much bias to create realistic data. And the labeling part, which is identify each attack and put a label on it, it's a really difficult, time-consuming task. So what we propose here is to study the network traffic generation of network traffic for attacks and benign. And the goal would be to provide a data set of complex APTs campaign, for example. And to maximize compatibility with existing solutions and further development of other solutions, we want it in pickup format, which is the best raw packet format for our work. So to do that, we propose to separate the generation in two parts. First of all, we want to generate the traffic for elementary procedures. So for example, on attack traffic, it refers to the, for example, mid-attack techniques or techniques used, so a CNC channel, data exfiltration, lateral movement, etc. And you could also include individual flows from benign traffic. So we've seen Kerberos, we have benign HTTPS traffic, etc. And on the second part, which is not part of this study today, it would be to have the generation of a full scenario that includes the attack timeline, the assets, and describing all it's going on, and generate the traffic for all of these parts of this scenario. And in that way, it will provide a data set with the scenario, that is the description of the data set, and provide labelization by design. So today we are interested on generating traffic for elementary procedures. So first we define which network traffic format to use to best align with PCAP format. We'll see that this format is not easily usable for generative models, so we are using representation learning. And then we'll finish by the network traffic generation, how to use a transformer architecture to generate traffic, and how we can condition this generation to generate specific class of traffic. So for this study, we used the data sets from Stratosphere Laboratory, from Czech Technical University in Prague. The advantage of the data set is that for malware traffic, they just deploy malware, just opening a link on an email and capture the traffic of, we recall 3 different malware, Emotet, Druidex, and Trickbot. So we have traffic for those 3 different malwares that kind of look like HTTPS sessions. And additionally, we used some capture of HTTPS traffic to try to make the difference between them. From this data, we used 2 different data sets. The unbalanced data set, which is more than 2 million flows of the 4 classes, and a balanced data set with 100K flows per classes. So, first of all, let's describe the network traffic format, which is really close to what Pierre-François used just before. But before that, let me just go through the literature. So, in the literature of network traffic generation, you can identify 2 main methods. The first one is the flow metric generation, so the net flow format that we just seen before. And this format is very useful because it provides the flow format, the flow granularity that can be associated with a label, but it lacks of packet details. So the net flow format is just a set of metrics. You have other works that extended the metrics per flows to hundreds of features, but we believe it will be better to have packet details. On the other end, you have some works on pcap generation or packet level generation that are the opposite, that provide good packet details for realistic traffic, but does not include these flow format that is useful to associate with an attack label, for example. So, what we've done is sorting a pickup into the different flows, so following the 5 tuple of IP addresses, ports, and the protocol, which is in this case only TCP. And we used a tiny packet format of just interval void time, payload size, direction, and flags. So the question of the payload was addressed earlier, but here in this case we are dealing with, a lot of encrypted traffic. So we only consider the payload size, and the generated payload will be randomly generated. So our representation of traffic is a sequence of packets. So it includes the packet details and the flow format needed for the labels. From this format, we can easily reconstruct a pickup, so all the header of a pickup, by first defining the endpoints we want by selecting random MAC addresses, IP addresses for the moment. And then we can fill the packets with our format, so the IAT, the direction that defines the endpoints, the flags and payload size, and additional header fields on TCP are calculated from those informations. So here we have defined the network traffic format. We are able to reconstruct a pickup from it, and now we're going to define the model we can use. So what are we doing here? We are not using out-of-the-box models, so we are building our own with TensorFlow and Keras. We are dealing with sequential data, a sequence of packets, so we are using recurrent neural network layers. And then we asked ourselves which architecture used to generate traffic. So first of all, we take a look at VAs that are basically outperformed by GANs. And GAN have trouble dealing with sequence of discrete data. So when you're dealing with categorical data such as flags and direction, it's difficult to generate directly with GAN such sequences. So that's why we are using representation learning. Yet another model to discover, the autoencoder. So I will be quick on this one, but if you take the case of images, you can see the autoencoder as a classification algorithm, or in this case, representing a data, in this case an image, into coordinates in the space. We call this space a latent space, and this kind of look like that. If you take, for example, this latent space of 2 dimensions, we can see an autoencoder that map each image of the dataset onto coordinates in this latent space. And what's interesting here is that we can train a generator to generate new data in this latent space, so generate new coordinates in this latent space. And by giving them to the decoder, you will be able to transform your generated latent coordinates into the original data format. So what we've done is first a baseline for comparison based on the work of Shade et al. That done the same thing using only sequences of payload size on IoT devices. So the idea here is to transform our flow, which is a sequence of packets, into coordinates into a latent space. In our case, it's a 32-dimensional space, so it's quite huge. But each flow is represented by coordinates in this space, meaning that a flow of 3 packets or 100 of packets is represented by a 32 fixed size vector. So one bottleneck of this approach is that we lost the size of flow in our inner representation. But then we can train a GAN to generate new latent coordinates and decode them back to a network flow. So now we'll talk about our main contribution. It's called the Netcliffizer. And the intuition was network traffic data is mostly composed of discrete and categorical data. So you have the payload, which is discrete. It's only 40 bits between 0 and 1,160. You have the direction, which is binary, and the flags, which are categorical. So the intuition here was, instead of learning a representation in a latent space of continuous vectors, etc., it's transforming a sequence of packets into a discrete sequence of vector. And this looks like our tokenizer converts text into sequence of integers for the neural language processing, and we call these discrete representation of packets netglyphs. So how does it work in details? It's more complex architecture of an autoencoder it's derived from a VQVAE for vector quantizer variational autoencoder. And basically the first step is transforming our sequence of heterogeneous features into a sequence of continuous vectors. So for each packet, it will associate a continuous vector. So this is a job of the encoder. Then comes the vector quantizer that will replace each of these encoded vectors by the closest one in what we call the codebook. It's a dictionary of all the netglyphs. And from this discrete representation, the decoder will be able to reconstruct the original flow. Here is to be noted that the codebook, the netglyphs are learned during training. That means we have a specific loss function that modify the encoder to produce vectors close to the one on the codebook, sorry, and the codebook learns to use vector close to the encoder output. So we have the encoder and the vectors in the codebook working together to be close to each other. So we analyze the two approaches by analyzing, first of all, the reconstruction. So it's, as it is an autoencoder, we can compare the input and the output of the model. And first of all, as it's difficult to directly study the whole sequence of heterogeneous features, we are looking at features individually. So for the two features, interval time and payload length, we perform the principal component analysis to compare the distribution of the sequence of IAT and payload for the original and reconstructed data. And here we can see that the distribution are not really similar for the payload, for example, and the interval time is just a subset of the diversity of the original data. And if we look at the categorical attributes, we have a lot of errors, almost around 15% for both direction and flags, which is, in this case, really bad because direction and flags defined key elements of the TCP connection. So compared to our approach, we can see for the distribution that the distribution of the two continuous and discrete attributes are really close to each other. So we have a model that learns a good representation and reconstruct accurately those two features. And on the intuition that the discrete representation would better represent discrete attributes, we have results on direction and flag reconstruction close to 0. So here are the number, or it's 8 errors on thousands of flows. So then we talked about, on the beginning, of using 4 different data sets. So we just compared by violin plots the distribution of reconstructed data from each classes, and we can see that our approach is much closer to the original distribution for each of those classes. So it kept a good representation for each of those classes. So our solution, by learning discrete representation, greatly increased the accuracy for all feature types that are continuous, discrete, and categorical. It's an efficient design because the netglyphizer model have 90% less parameters in terms of number of parameters. And while the baseline methods does not keep the size of the flow in the latent representation, our method keep the consistency of this length. So a flow of 3 packets will have a latent representation of 3 netglyphs, which is better for the reconstruction. So now, let's talk about network traffic generation now that we learn a good representation. So to do that, we interested in transformers, that popular model, the buzzword of the moment, that can generate really high quality text. So if I take the example of the text to begin with, this method uses tokenizer to transform text into sequence of integers. And then you can use what we call a transformer decoder only architecture as autoregressive model to predict the next token to use. So here, the output of the transformer is the size of the dictionary. So here, the size of the output of the transformer is the number of words in the dictionary. And you have the probability associated for each other, for each of member of the dictionary to be the next token. So our approach is pretty similar because we have the netglyphizer, which is netglyphizer encoder that is able to transform our sequence of packets into a sequence of netglyphs indices in this codebook. And that means we can use a transformer to predict iteratively the next netglyphs to use, then re-injecting the generated sequence and predict iteratively the next netglyph in the sequence. And what's interesting about this architecture is that you can prefix the initial sequence with a label. So here it will be a number between 1 and 4 to represent the 4 traffic class we are using. And by prefixing the sequence, the transformer will be able to predict the next token, taking it into account the label provided as in input. So to do that, we use this time the balanced dataset, which is composed of 100K flows per classes, to extract the original dataset in netglyph format and prefix each of the flows with the associated label to train the transformer. Once a transformer is trained, we can generate new instances of netglyph sequences that can be decoded in flow X, so in a new generated flow. So now let's take a look at the generation results. For comparison, we took the baseline representation learning we've seen before and used a GAN to generate new latent representation to have a baseline of comparison. And we can see that the baseline coupled with the GAN perform worse accuracy for the similarity between the original and generated distributions for the AIT and payload length. So our approach better preserves the original distribution. We can take a look also at the distribution between the different classes, which is also most of all more compliant with the original distribution on our generated dataset. And to finish, we cannot use the method before to evaluate the direction and flags. So we perform some protocol analysis and protocol compliance. So here are the results. So we identified 6 different scenarios. So we looked at the fully established connection, so a complete 3-way handshake. We have the connection refuse, which are scene reset flows. We have also connection attempts, like a sequence of 3 scene. Then we have on the dataset, we have some 3-way handshakes that are malformed. And then we implemented the TCP state machine to see whether the clients and server are reaching the closed state at the end of the TCP connection. And what we can see here is that our approach is more accurate for all these scenarios than the baseline. The baseline is always using full 3-way handshakes in that case and have trouble reaching the end of the connection. So to conclude, we have netglyphizers that shown promising results in representation learning for network traffic. A transformer can be used to generate new netglyph sequences and can be conditioned with the label we want for the generated traffic. And this generated traffic can be converted to the pickup format. As future work, we want to deeper analyze the net lifts because they are learned during the model training, and we want to analyze a little bit the distribution and what choice the model made to choose those net lifts, for example. We want to see the impact of these generated flows on traffic classification. Does it improve it? Does it, or does it not? And at the end, there is the second part of the work, working on the generation of attack scenarios. And a network talk couldn't end without a Wireshark. So here it is, a flow fully generated by our method. Thank you.
Ah, yeah, do you have any questions? Don't be shy. He's a nice guy, I know him. I know him, sorry. Maybe that's the similarity of the topics. I'm sorry for you.
Hello.
Vincent, you're doing networking.
Bah oui, PF. PF. Which method is the best?
Is there a public implementation of methods or not yet?
I'm currently working on it, to making it public, because it's kind of a mess in all the Python program right now. So, but yeah, the idea is it's to make it open source and put it on GitHub. I don't know when, but it's the objective.
Okay, thank you. So I think we have to stop here. So thank you, Gavin. So it's a break. Don't forget, there is a workshop here at 1 o'clock, I think. Is in this here, the same workshop as yesterday, and we start the conference at 2 o'clock. Okay? 2? Yeah.